Swayam Prabha. Digital India. Educated India.
Welcome back. We were discussing about the combustion of double base propellants. In this lecture, we will try to see if we can derive some mathematical equation of the linear burn rate of double base propellant. But before moving into the evaluation of burn rate, we will try to spend a few more minutes on the dark zone, which is also known as the induction zone. Let us try to see the residence time of the dark zone. Sometimes it is termed as the reaction time of the dark zone, and what are the influencing factors of this dark zone, and then I think we can move on to the evaluation of burn rate of double base propellants. So, in the previous lecture, I think we had already seen that the dark zone is very much dependent on the pressure and temperature, but we also need to remember that the dark zone is very much dependent on the concentration of NO, not the NO2, not the NO2. So, if we try to see how the concentration of NO is going to influence the residence time in dark zone, sometimes it is denoted as tau d, which is determined from the length of the dark zone divided by the average gas velocity of the dark zone u d. So, here we are saying that L d is the thickness of the dark zone and u d is the average gas velocity in the dark zone. Now, the residence time can also be considered as the reaction time to initiate the luminous flame zone, or the ignition delay time between the feed zone and the luminous flame zone, as we have already discussed in the previous lecture. Now, if we apply the overall continuity equation, we can actually find out the average gas velocity of the dark zone is going to be equal to the density of the propellant into burn rate by the density in the gas density in the dark zone. Now, we can also get some more relationship by using the equation of state, where we can see the rho is P by R T. So, if we just apply the equation here, we can actually get the residence time or the reaction time of the dark zone is going to be equal to tau d is going to be equal to P into L d by R into, here we can write R d into temperature T d. So, here we can say the temperature in the dark zone is R d, gas constant in the dark zone is R d, and here R is the burn rate or linear burn rate or linear regression rate. Rho d is the density of the gas in the dark zone, rho p is the propellant density, R d is the gas constant, now as we told earlier that the dark zone reaction products the dark zone reaction producing luminous flame is kind of dependent on reaction involving NO, not the NO2. The reaction time in the dark zone can be plotted with the function of as a function of the concentration of NO Now, if you look at the reaction time in the dark zone tau d in millisecond, one can see as we increase the concentration of NO, the dark zone reaction time or dark zone residence time is going to decrease, because the concentration of NO is going to influence the reactions in the dark zone. So, eventually that will reduce the reaction time in the dark zone. Now, if we increase the pressure, for a increasing pressure we can see this is also going to change. So, that is like P increases, as we already mentioned earlier that if the pressure increases, in fact, for a high pressure dark zone ceases to exist, dark zone will be almost eliminated. So, the concentration of NO and the pressure are going to influence the residence time in the dark zone, or eventually this will influence the ignition delay time between the primary reaction zone and the secondary luminous zone or the luminous flame zone. So, this part we also need to remember in the context of the dark zone, that how the residence time of the dark zone is going to be influenced by the pressure and the concentration of NO. Now, with this discussion I think we can proceed further and try to find out some mathematical relationship of the burn rate, what we just said, that the linear regression rate or the burn rate, which is generally given in terms of like millimeter per second, because if you recall in our discussion that in case of solid propellant it is generally burned normal to the surface, and the burn rate is considered to be like how much length is regresses over unit time. So, if you consider like a n burning propellant, so it is going to regresses over time. So, the R is going to be like L by delta t, like how much amount of length has regresses over a time period delta t. So, it is basically the length divided by time. Now, there are various instruments which are various experimental setup have been used to determine the regression rate or the linear burn rate. One such instrument is called Crawford burner. I think we have already mentioned earlier that we can conduct the experiment by considering a closed chamber filled with nitrogen, and we can let the one small strand of propellant burns, and the length is going to regress over time. If we inhibit the propellant surface circumferentially, if we let the burning to take place only from the top of the propellant, then at a certain time period, after a certain time period, it will burn a length of L, where we have put the fused wire. So, based on the timer unit is going to give us the time period delta t, where the first and the second fused wire will get cut, and since they are already impregnated at a particular length, from there we can actually find out the regression rate L by delta t, and that we can do it for various pressure. So, this is like a different pressure, it may be like P1, P2, P3 and so on, and one can actually plot it, and we can find out the relationship between the pressure and the relationship between the regression rate and the pressure. Now, how the regression rate is going to very much dependent on the pressure, we try to understand through some simple analysis. So, in order to do that, we will just need to consider a small control volume in the feed zone, because we have said that the major reactions will take place in the feed zone. So, feed zone is kind of a very important consideration, and the heat release is going to take place in the feed zone. So, if we consider a small control volume in the feed zone, and if we consider the energy balance there, and from there actually we can try to find out how the regression rate is going to be dependent on the pressure. Okay. So, let us try to look at that. So, let me just draw one simple zone wise diagram what we have already did earlier. So, we have like preheated zone, we have foam zone or solid state reaction zone, then we had feed zone, then we had dark zone, and finally, we had the luminous zone. So, for the evaluation of burn rate, we are trying to consider a small control volume within the feed zone. What we said that, let us say we consider a control volume at a distance x, the length of the control volume is dx, the cross sectional area of the control volume is unit cross sectional area. We will try to see we consider the energy balance across the control volume in the feed zone. Now, how do you do that? We know that the heat transfer is going to take place by through conduction. We can consider the heat conducted heat conduction increases from heat conduction into the control volume. We can determine from assuming the heat conducted along the x axis, and the heat conduction is going to increase from this surface is going to be minus kg dt dx at x, 2 is going to increase to minus kg dt dx plus ddx of kg dt dx into dx. This is going to happen at x plus dx, because this is the distance x and this is x plus dx. Okay. So, this is what about the heat release over our distance dx. If we consider the volumetric heat release is let us say q chem, which is volumetric heat release rate joule per meter cube second. we can get the heat release over a distance x. We can, and we know the unit cross sectional area. So, this is going to be q dot km into dx. Now, what about the net heat transfer to the control volume? You can simply this minus this. So, you can get the net heat transfer from the, sorry, this should be outside of the bracket, negative sign. So, the net heat transfer into the control volume is going to be equal to minus ddx of kg dt dx into dx. By the way, kg is the thermal conductivity of the gas, conductivity of the gas. All right. So, the heat transfer to the control volume and the heat generated in the control volume, what is going to do is going to increase the enthalpy of the gas flowing through it. So, we said that heat transfer to the control volume, heat generated in the control volume q dot km into dx, heat transfer was this is going to increase the enthalpy of the gas flowing through it. So, if the enthalpy of the gas is like, we say like rho g into u g into C T, that is going to increase to rho g into u g into C into d T plus d T. Now, I will tell you what is u g and what is rho g. Rho g, u g, you can understand that they are the density of the gas and the, so rho g here is the density of the gas, u g is the one dimensional velocity of the gas. So, basically the enthalpy of the gas flow through the control volume increases from rho g u g C T to rho g u g C into T plus d T, where T plus d T is the increased temperature and C is the specific heat of the gas. Okay. Now, from the steady flow energy balance for the control volume, if we just considering the steady flow for the CV control volume, what you can write? We can write the heat transfer into the control volume, which is ddx kg dt dx into dx plus the heat generated within the control volume, which is q dot km into dx, is going to be equal to rho g u g C T plus dt minus the flowing enthalpy is like rho g into u g into C into T. Okay. because the enthalpy of the gas has changed from rho g u g C into T to rho g u g C into T plus dt. Now, if you simplify this, we will end up getting Kg, we are considering Kg as the constant thermal conductivity of the gas. This will come as d square dx square plus rho g into u g into C into dt dx is going to be q dot chem. So, we have this equation. Now, we have this ordinary differential equation. So, if we want to know the boundary condition here, if you want to solve this equation, we need to know the boundary condition. So, what are the boundary condition we have? We can look at what we already understood in the previous lecture, that we said that at x equal to 0, which is part of the propellant. So, we can consider that foam zone is still the solid phase reaction is taking place in the foam zone. So, it is here we can say it is x equal to 0. So, the beginning of the feed zone is kind of x equal to 0, which is right at the end of the foam zone. So, that is x equal to 0, and x equal to 0 we said the temperature was surface temperature, which is Ts. So, we can say the surface temperature is Ts, and end of the feed zone, which we have said that temperature may be Td, because the dark zone has just started. So, we can say the temperature at x equal to 0, T is considered to be Ts. At x equal to L, let us say this is end of or edge of feed zone, this we can say temperature is going to be equal to Td, let us say. Edge of feed zone means starting of the dark zone. These are the two boundary conditions we have. So, basically the temperature profile will be like this. We have like this is like the distance x. So, we had the starting temperature from Ti to initial temperature to it will reach to propellant surface temperature Ts, and then eventually it will go to like the Td. Sometimes it is termed as T1 also, since we use the dark zone temperature Td. So, let us consider this as the Td. So, this is the end of the feed zone or the edge of the feed zone. After that, the temperature will remains almost constant in the dark zone under the condition of lower pressure ranges, and then in the luminous zone the pressure will the temperature will again increase. Okay. But since we are considering only up to the feed zone, so we are considering the edge of the feed zone, which is like let us say length of the feed zone is L. So, at x equal to L, the temperature is T equal to Td. Now, in order to solve this, what we need, so we know the temperature distribution like this for a given, I mean we can have this temperature distribution for a given value of Ug, and if we have this if we have this given value of Ug, Q chem is also if it is specified, we can try to solve this and we can actually get the temperature profile something like this. Now, we have to understand certain things here, that heat release rate which is like Q dot chem is kind of very much influenced by the chamber pressure or the pressure and temperature, and of course, is going to proportional to the reaction rate. So, if we look at the Arrhenius equation there, that Q chem is going to be finally is going to be very much influenced, or it will depends on pressure and temperature, and is going to be proportional to somewhat like A p to the power m e to the power minus E by r 0 t, where E is activation energy. I think we know this equation from the Arrhenius equation, where k equal to A into e to the power minus E by r t. That is the equation I am writing here. So, this is capital E is the activation energy, R is the gas constant, and A, E, R kind of M are kind of constant for the given reaction. So, we can see here that it is very much influenced by the pressure of the chamber, which is the P. Now, what about the value of u g or the gas velocity? The gas velocity will be decided by how the gas evolves from the degradation of the solid propellant in the foam zone, because ultimately degradation of the solid propellant is going to decide the gas evolved in the foam zone, because if you recall in the different zones of the combustion of the double base propellant, foam zone is very much part of the propellant surface, where the degradation or the solid phase reactions are taking place in the foam zone. So, as the reactions taking place here, they are basically breaking the bonds between like CO and NO2, and they are actually going to liberate the gas phase species here from the foam zone. So, the gas velocity u g will be kind of decided by the rate at which the gases get evolved in the foam zone due to the heat transfer from the hot gases at the propellant surface. So, basically this is going to be influenced by the heat transfer from the propellant heat transfer to the propellant surface from the feed zone, and the degradation of the propellant will eventually lead to the formation of gaseous species. So, in a simple term we can say that the gas velocity u g is going to be very much depend on the gases being evolved in the foam zone due to the heat transfer from the heat transfer to the propellant surface or at the propellant surface. So, we can say if we know the linear regression rate, let us say r, that r is the regression rate at which the propellant is regresses, or the length of the propellant regresses over a unit time period is r. We can actually make the mass balance equation. We can actually write the mass balance rate at the surface, that the surface is going to regresses. So, for a unit cross sectional area, we can say that mass balance rate at the surface, what you can say? We can say that density of the propellant is rho r into unit cross sectional area 1 is going to be equal to the gas evolved, like gas flowing through the feed zone. The density of the gas is rho g, u g is the gas velocity into unit cross sectional area 1, where r is kind of representing of just like a velocity like meter per second or millimeter per second. So, in a sense r is regressing over time, like the propellant is regressing over time. So, millimeter per second. So, if you look at the cigarette like strand, or just if you consider the cigarette burning, what is going to happen here, as the person puffs it through it. So, this will keep on burning, So, length is going to regresses over time. So, it is eventually like this. So, the regression rate is something like that, which is giving you the linear burn rate. So, if you just do the mass balance rate at the surface, we can actually end up getting the relationship that rho p into r is going to be equal to rho g into u g. So, eventually we are going to relate the r with respect to other parameters. Now, somehow if we replace u g in terms of rho p into r by rho g, we can actually get into the equation here where my r is going to involve. Now, one can actually understand that a unique solution for r. So, let us say if we try to put this in this equation, and we can write k g d square t dx square plus rho g into, instead of u g we can write here u g as rho p into r by rho g. So, we can write rho p into r by rho g into c dt dx, which is going to do q dot chem. Rho g you can cancel out. So, here we can actually include the r in the equation. Okay. In this equation now we have involved r there, which is the linear regression rate. Okay. Now, we should understand here one thing, that this equation is very much involved, like it is not so easy to solve this equation straightforward way, in a straightforward. Rather, if you look at the q dot chem, which is the heat release rate or volumetric heat release rate, which is very much dependent on the pressure and temperature, or in a sense we can say it is very much is going to be very much influenced by the pressure. The other parameters which are like, so the heat transfer, the thermal conductivity kg is involved there. So, we can actually have the value of gas thermal conductivity, but without knowing the property of the gas, it is very difficult. What are the different type of gas mixtures present there? What is the temperature profile we said here? In getting the temperature profile is also kind of very difficult. So, in a sense we can say that unique solution for R is kind of is going to be very involved, or rather we can say that the unique solution of R, which is going to satisfy the temperature profile at the boundaries and heat balance within the foam and feed zone, is going to give us the burn rate of the propellant. Okay. If we somehow solve this equation, which is going to satisfy the criteria of the temperature at the ends and the heat balance within the foam and feed zones, that would give us the linear burn rate or the regression rate of the propellant. Now, the process of having the solution is going to be very involved, but one thing we can notice that the rho g, u g and q dot chem are somehow very much depend on the chamber pressure or the pressure, that the density of the gas, the velocity of the gas, the heat release rate q dot chem is somehow is going to be influenced by the chamber pressure. So, in a sense we can say that R is going to be very strong function of pressure. Okay. So, we can say that my regression rate, linear regression rate R is going to be a strong function of pressure. So, from there actually we can say that it is going to be, it is like an indirect way of realizing that the regression rate or the linear burn rate is going to be influenced by the chamber pressure, and that way it is generally written that R is going to be A p to the power n. This is the burn rate law, very popular burn rate law used for solid propellant, where A takes care of the initial temperature, composition of the propellants and other characteristics, and n brings the pressure effect, whereas the n is the pressure index. So, n brings the pressure effects of the propellant, which are kind of dependent of the combustion process. So, this is the famous burn rate law or the Villiers law, sometimes it is termed as the Saint-Roberts law. The value of A and N are going to be obtained by considering the experiments and using the curve fitting. As we have already said that using the Crawford burner test, one can actually try to get the data of burn rate for various pressure P1, P2, P3 and so on, and from there if we do the curve fitting we can try to find out the value of A and N. Okay. So, I think with this note we will close this lecture today. I think we can continue the burn rate law in the next class onward. Okay. We will try to understand what are the other factors, the pressure range, how do we really know that at what pressure range, how it is going to work, how we plot this burn rate versus pressure, is there any difference for different type of value of N, whether there is any influence of that. So, we will look at those parameters in the next lecture. All right, thank you.